Okay, so let's look at some questions involving Newton's laws and cars. So we've got a front-wheel drive car travelling at constant velocity, and the forces acting on the car are shown in the diagram. So we've got two normal forces acting upwards from the road. We've got a driving force from the front wheel of 400 newtons. We've got some force Q, and we've got the weight force 10,000 newtons. Q is the force of air on the moving car, so a drag force, and P is the total upward force on both the front wheels. Calculate the explanation the size of P. Well, if the object is driving at constant speed and it's going like horizontally like you see, the upward force must equal the downward force. Or another way of saying that is the resultant force must be equal to 0. So what that means is that P plus 6,000 must be equal to 10,000, or that P is 4,000 newtons. Okay, so state with explanation the size of Q. So we're going to use exactly the same logic. The constant velocity, so the resultant force is 0, so Q must be equal to 400 newtons. Calculate the mass of the car if we're on Earth with G equals 10. So weight force is mass times gravitational field strength. So we're going to rearrange that. We saw from the diagram the weight force was 10,000, so we can clearly see its mass is 1 ton or 1,000 kilograms. The 400 Newton driving force to the left is suddenly doubled. Calculate the resultant force driving the car forward. So now there is 800 newtons forward, 400 back, giving a resultant force of 400 newtons. Calculate the acceleration of the car. So this is what Newton's second law, F equals ma, does. So we rearrange to calculate acceleration. We know what the resultant force is, 400. We know the mass, so we can get the acceleration. Draw a sketch graph showing how the velocity of the car changes with time. Start your graph just before the driving force is doubled. So here's our velocity time graph, and it was traveling at constant velocity, so it's going to be at the velocity is going to stay the same over the period of time, and then we've got a constant resultant force of 400 newtons, a constant mass of 1,000 kilograms, so we're going to get a constant acceleration, which is a straight line graph. So passengers in a car are advised to wear a safety belt. Explain in terms of Newton's laws how a safety belt can reduce injuries. Okay, so Newton's first law states that if no resultant force acts, the velocity of an object does not change. And this is what's critical. So when the car stops, the car's velocity decreases because of the brakes being applied, but there's no force acting to stop the person. So the person continues with their original velocity, which means they smack into the windscreen, okay? And that's going to hurt and cause injury. So with a seatbelt, there is now a force to decelerate the passenger. And it will keep the passenger in the same position in the car and stop them hitting the windscreen, hence preventing them being injured. So explain how using a crumple zone to increase collision time leads to reduced passenger injuries. Okay, so acceleration is rate of change of velocity. So let's say I'm traveling along at 10 meters per second and I need to stop. So I'm going to go to 0 meters per second. There's nothing I can do to decrease the change in velocity because that's determined by how fast I'm going. But what you can do is increase the time. So if I make that change in velocity over a longer period of time, the acceleration is going to be smaller. And Newton's second law says a small acceleration means a smaller resultant force acts on you, and a smaller force means there's smaller chance of injury. Okay, so that concludes these Newton's laws and cars solutions.